thanks for coming, Harsh, to this mock interview. This will be a Leetcode style interview. Do you want to just quickly give a quick introduction about yourself before we get started?
Yep, sure. So my name is Harsh. I'm a new grad from U of T. Currently preparing for Stripe on-sites. And yeah, interned at Amazon last summer.
Awesome. Are you currently in Eastern time?
Yeah, I am. So it's like
Uh,
8 p.m. here.
oh, you should have told me. I didn't know what time zone you were in. Well, doesn't
Oh,
matter.
it's all
We're
right.
all here now, so let's get right into it. Great. So you're in the coder pad, right? I see you're here. Yeah, that's right.
Yep.
What's your preferred language?
Yeah, let's just stick with Python.
Okay, great. We can stick with Python. You can change halfway as need as well if you want to do something else in different follow up, but just know that the code will not transfer between languages. So decide early on, otherwise you might
Okay.
lose some stuff. Okay, so I'll
No,
be
I'm good with that
dictating
one.
a problem description to you, so you're free to take notes on
Mm-hmm.
the coder pad as I talk, and feel free to pause me and stop me. If you have any questions. We'll be targeting for a likely a 45 to 50-minute technical portion, and I'll leave 5 to 10 minutes at the end
Mm-hmm.
for feedback. Usually in an interview, right, the last bit will be for you to do introductions or for you to ask questions, but we'll be skipping that today. So the last 5 to 10 will just be giving some feedback about the session. Any concerns
Yep.
before we move
Sounds
on?
good. Uh, no, you can start.
Okay, let's get started. Okay, so this problem is going to be about pathfinding. Okay, so in this problem,
Okay.
I want you to write me a function, and it's going to solve a counting problem. Well, one of the counting problems. So this the input to this function will be a m by n grid. Okay, and in the top left corner, which is the 0, 0 coordinate, that is the starting location. Okay, so it's a location of where a robot starts in this grid. Okay,
Mm-hmm.
and the robot is trying to move to the bottom right corner. That will be the index of grid m minus one, n minus one,
Mm-hmm.
and the robot is only allowed to move down or right at any given point in time. Okay, so to complicate things a little bit. Okay, there is a obstacle. Okay, there's an obstacle, and an obstacle is going to be marked as, for example, in the grid, it's going to be grid in numbers, let's just say. Okay, so if there's no obstacle on that point, there'll be a 0. If there is an obstacle at the point, there'll be a 1. Okay, and the obstacle, obviously what it means is that a robot cannot take a move that brings it onto an obstacle. Okay,
Mm-hmm.
so the purpose of this function is to return the total number of unique paths the robot can take to reach the bottom right.
Okay. Also, by the way, are you gonna paste the question in, or
Now this will be
is that?
this will be dictated, so this will be more like a whiteboard style interview.
Oh, interesting.
Do you want me to go over some
Uh,
parts again?
yeah, like I was
No worries.
expecting that.
Yep.
Uh,
No
yeah.
worries. So this will be
So yeah, we start.
yep. So I want to write me a function. This function will take in a grid that is m by n. Okay. So this would be m by n grid. The starting location is 0, 0. That is the top left. The ending location or the goal is the bottom right, which is m minus one at n minus one. Okay.
Mhm.
The robot can move down or right only, so it can't move left or up.
Interesting.
There are additionally obstacles on this grid. No obstacle is marked with a 1. No obstacle is marked with a 0. The goal of this function is return the total number of paths the robot can take to reach the bottom right.
Path from zero, path from start. Okay, sounds good. So I'm assuming it's like total number of unique paths from start to end.
Yep.
Uh, okay, so just explaining my immediate thoughts. So I could do this recursively. Um, where so at any given point, let's say if you're at I comma j, like at any valid point. So you basically have like two options. If there's no obstacle to the right, like you can move to the right, and and yeah, you can probably sum up the number of paths. Also, if you like go down, by the same time, there might be multiple paths to start. from that. So as in, let's say from 0, 0 to I comma j, there might be multiple different paths. So we might have to like memorize things. So it might be easier if I just like start an example. So let me do like a 4 by 4 thing. Let's see, just put in some obstacles. Let's say if I start here, I can either go to the right
Mm-hmm.
or to the left, but like let's say if I'm at this point, I cannot go to this.
Mm-hmm.
But let me like talk about this point, for example. So there's like two different ways that it can start from. So you can either start from this thing or you can either come from this or this, but we want to make sure that we don't count them uh twice. Or let me see.
Can you elaborate on what you mean by counting twice?
Yeah, like I'm just worried about the fact that at some point, I mean, I'm trying to make sure that I don't repeat the same paths again. There has to be some way for me to like differentiate them. I'm just trying to think of
Okay.
what I can do for that. Oh, so yeah, here's what I mean. So let's say, um, yeah. So let's say if you end up at this point, like there might be like multiple different paths that end up at this point. So you don't want to repeat the work, and you know there's like just one path that goes from here to the end, right?
Mm-hmm.
There's
Okay.
just one path that goes from here to the end.
Yeah.
So we can just like store that once, and it's kind of like deep a little bit, as in like we'll have a hash map on the top. We'll store the number of paths from a given point to the end. So for example, n minus 1 to n minus from n minus 1 comma n minus 1, that's just gonna be like one path. So it's just like itself. Um, I mean, we can either do this bottom up or top bottom. I mean, just if I start from like the end, so there's like one path that goes from this point to this point. There's also one path you can just go down at this point. You can't go right. So that's that. And yeah, eventually we'll just like work our way to the top left.
And is this approach you just talked about, is that bottom up or top down?
This would be bottom up. We could also do it the other way around. That might be a little easier actually. Like if you're just doing it recursively. Um, yeah, I can start with a recursive solution first.
Okay.
The matrix is a list of integers. So let's say if I have a visit function, takes in the matrix. I'm just gonna copy this thing. And then let's comment shape. So the matrix. And just doing some edge cases. All right, so we will start counting paths by visiting the start. Um, so let me just have like num paths, and I'm just gonna add. So I'm just gonna hardcode like a base case. So
Sure.
num paths of n minus one, comma n minus one. That's just gonna be one. And let's say if I call visit, on 0, comma 0. Then eventually the answer should be like that's 0, comma 0. Um, and we will like just populate this thing. And first of all, I'm just gonna check that if I know I comma j is is in paths. I'm just gonna return that. Otherwise, it's- otherwise I'm gonna see if I can visit something. Program paths. Mm. So if let's say I is uh less than I is not. So I'm just checking the boundary conditions.
Okay.
I just want to make sure that I can actually go to the right. So in that case, if I is not equal to n minus 1, in that case, I'm just gonna do visit. I'm actually gonna return the answer, so I can just do that. Matrix of I plus 1, then j. So since we're like indexing, this is the first index that's like going down,
Okay.
and the same thing again here. If j is not equal to that, I'm gonna move the column, so I'm gonna go right in this case, and then I'm gonna set the this thing. So I'm gonna j is equal to current numpads. And I'm gonna return the current numpads, and I'm just gonna make sure this thing works. We don't have n here, so let's do n as vertical length of matrix. Okay, so I'm just gonna try to think of this
Okay.
from the end. So eventually, like let's say we hit the end.
Mm-hmm.
In that case, let's see what's gonna happen. So we'll just go down this path if n minus 1 comma n minus 1 should already be there. So this thing is equal to 1. And then let's actually like we didn't, okay, I made a big mistake that we did not consider the obstacles. Again, we should just add like a condition here. So if I is not equal to n minus 1 and matrix of I plus 1 and then j is not equal to 1.
Mm-hmm.
So that means the thing that I'm gonna go to is not equal to 1.
Okay.
Also, I think probably ask, are we guaranteed that the start and the end are not obstacles?
Not necessarily.
So in that case, like, would you expect to have like no paths?
No pass. Yes.
Okay, in that case, like, we'll have to change this. So I'm just gonna add it to there, but so the same thing happens here. I feel like there's definitely a better way to like handle this case,
Mm-hmm.
but yeah, let's just go with what we have. So we'll need like two edge cases for the
Okay.
yeah. I'm just gonna do it together actually. Matrix of matrix of if this is equal to 0 or matrix of layers is actually click something. Oh yeah, that sounds right. I realized my dark mode was on, so like I couldn't see the cursor for
Oh,
so long.
okay.
But yeah, okay, I can at least see the cursor now.
I think this thing has a built-in dark mode for your info.
Yeah, I just like disable the extension. So yeah, it's good now.
Okay, okay.
Okay, let's look at this. So this base case is good. So I mean this is actually wrong. This is one or this is equal to one. And so if we know that the start or the end is the obstacle, like there's like no paths. Uh like I'll try to like change the code eventually so that I don't need the space case. Like it should be natural in the solution like somehow.
Mm-hmm.
But if that's not the case, we'll just go ahead and set the end to just have one path,
Yeah, that's totally fine for
and
now.
then yep. Okay, let's see what else is missing in here. So let's say we go in here and then total number of paths. So I mean maybe I should do it so that if I comma j is an obstacle, I can just return 0. That's probably a better way to do it. Uh, well, let's see if this thing works. Mm, Okay, so let me just go through this example. So just going from bottom up. I mean, I know the solution is in bottom up,
Mm-hmm.
but like we'll hit the space case. This is gonna be equal to. So this is not 0, so we won't like hit any of this statements. N minus one, comma n minus one is like just gonna be 1. And then let's say like let's talk about like this cell. So so if you like look at this, it's not gonna go in here. Uh, so in this case, like we'll just go down one of these paths, and so yeah, so visit is gonna return 1 in this case. So we know there's only one path from like from this point, and yeah, I think it should be fine. And yeah, for example, this case, so we know from this point there's just one path. So you just like go to the right and then you go down because we have an obstacle here. So even in this case, even though like I comma j um is not like n minus one or n minus one, uh, we'll still like hit one of these statements. Like one of them is equal to one. So we'll just go to the right. Uh, yeah, I think it looks good. Let me just like run a smaller example. So just like a really s- basic sanity test case. I'm just gonna build this thing. So this
Is that
should
for the
have like
base
no
case?
paths.
Is it
Sorry?
is A the base case?
Yeah, pretty much it's a
Oh, okay, okay,
use case.
okay. That's fine. Yeah. We can, for the purposes, we can skip the base case. We can just go to the real case. Yeah, that's fine.
Oh, yeah, alright, we'll not run it
Yeah,
then.
we have it already, but just
Uh,
for your future, we don't. I don't care about the base case, the edge cases for now.
okay, alright. So let's try like a really simple example. In this case, it's like just there's one path.
Mm-hmm.
So if we just do count paths of b from this should be one. Okay, there's one. Let's try a bigger example. Something with more than one path. Uh, Okay, this is a, let me just like put a multi-cursor. Nice.
Nice.
Oops. Okay, so I'm gonna have to add a bunch of ones, otherwise there's gonna be so many paths. Let's make sure there's like not many paths. Uh, okay, so I can see can just go down and right. So there's still just one path. Let's just like make more than one path. So it's still yeah, there's definitely more than one. So there's one, there's two. So like if I just like look at the most up the most uppermost part, so
Mm-hmm.
there's like one path from here.
Yep.
That's one path. Another path is like you go down and then you go right and then you take this path. That's two. And another path is like you go down, down, and then I think there's three paths if I'm not wrong.
There should be more than three, right? The variant for here is two, right? That means this is also
Yeah.
two. No, this is more than two, right? One. No, this is two. I'm not. I'm tripping. This is two. There's more than two ways to reach here, right? So it should be at least two plus more than two here, right? I mean, we can see program returns. We can see what the
Yeah, we can
violation
just
is.
see what happens. Can probably just inspect the numpaths thing. So see, and I'm not gonna print paths. All right, five. So mm, 3, 3 is ooh, one, which is right. Let's look at 2, 2 is one again. That's right. And then 1, 3. So 1,
1, 3. 1, 3 is a rock. No.
yeah, it should not be
What is your What is your
3.
1, 3? So you said your one comma. You have no 1, 3, right? Yeah, you have no 1, 3.
Yeah, I mean it should be 0 in that case,
Well, do
right?
you even set it if it's a rock?
Yeah, like I think I mentioned this, but what's happening is like we don't really check I comma j. We really check the next one. Uh, so I think it might just be easier if we like remove these conditions and
Well, hold on a second. Before we start editing your code, what's the correct answer for this puzzle? Have we cleared that up yet?
okay, let's see. It's like okay, let me just start. I'm gonna start like writing down the numbers in the script. So this is so just like imagine all these numbers have just the number of ways to get there. So this is one, and then this is also equal to one. This is also equal to one, and now this is also one because you can only just go down. Uh, this should also be equal to one because you can only go right. This should be two because you can go to the right and to can go down. Let's see. This is zero, which is right. This is again two. This is this is one. Yeah, this is one. This is three, and this is five. Yep.
Mm-hmm.
So five is the right answer.
Yep. I agree with that. That's fine. Um, What are we changing here in the code? I saw you were trying to change something.
Yeah, so we can definitely improve this. So what's happening is I'm checking the next element that we're gonna visit.
Uh
So
huh.
I'm checking like I plus one and j. Instead of doing that, we can just check I comma j. And we actually don't even need this thing, for example, if I is not equal to. So what I'm saying is we can just like remove these things and we can just do something like if if I equals to like n minus one, let me just get that up there, or j equals to n minus one, or matrix of I comma j is equal to one. In this case, just return zero. I mean, I'll actually set it to zero and then I'll return it. So I was saying something like this, so we don't like need these things. Like we don't need the conditions on that,
To be
so we can do
to be
something like
explicit
this.
here, uh, you're saying this is an improvement. Improvement on. Can you be specific on what you're improving?
So yeah, if you inspect the numpad, like one comma zero should not have been three. I don't know how we got that three, but
One comma zero. What is one comma zero? One comma zero is three. Okay. One comma
so yeah,
zero
that
should have
should
been three,
not.
right? One comma zero should have been three.
Oh yeah, never mind that. Okay, yeah, you're right. But yeah, I think I don't. Yeah, I guess we didn't improve much then. Uh, so I think we regressed.
Was that for code cleanliness, or do you think it was for correctness? I want to be clear about this one, or like efficiency, or like what?
No, so it was not for efficiency. Like it will be the same complexity definitely. It was for like code cleanliness definitely, but it definitely backfired because yeah, everything's here at this point.
Okay. Are there any other concerns with the code you have right now?
Yeah, I'm just gonna go back to the previous code.
Okay. Okay.
Yeah. So yeah, any other concerns at this point? No.
I'm happy to do some analysis on
We
this
can
one.
probably,
We can talk about if you're happy to
yeah,
correctness.
we should.
We can move on from that. I want to talk a little bit about
Mhm.
the time and space complexity for this solution.
Definitely. So let's start with like this the space complexity.
Okay.
So this is gonna be, so let's just, I'm gonna write down the number of elements is like n square because you have an n by n grid. So the space complexity is O of n square because like in the worst case, like everything is free, so that you have like no rocks, and you'd basically have to like remember the count of every single position. Um,
Mhm.
so you would have like n square of these um key value pairs,
Mhm.
and the space so that and the time complexity would also be the same O of n square. This is because like we do store the work we have already done before. So visit is gonna be called like just once for every tile, or it would be like just go in the first if statement. So we'd just like hit this case.
Mhm.
So we won't do like any work, any additional work in that case. So so yeah, just because like we memorize the function, like it's gonna be O of n square again. And I'm gonna like this is gonna be the most optimal solution because like even in the worst case, you'd have to go with an entire input.
Okay.
N square is again the number of elements that we have, so
Mhm.
this is a linear time solution.
Okay. One thing I wanted to ask is let's say for example, I say that there are k obstacles. Okay, is that something you can incorporate into the analysis?
Sure, we can try. So, what does it mean when we have an obstacle? Uh, uh, uh. So, obstacle just reduces the number of paths that we're gonna take. So, it's only gonna improve the time complexity. Uh, because as soon as we see the obstacle, like anything to the right and anything to like anything down, it, it's like just eliminated. So,
Well, hold on a second. Uh, Everything to the right and underneath the obstacle is eliminated. Can you clarify what that means?
oh, actually, yeah, yeah. I mean, like once you land on an obstacle, like you don't bother like traversing from that obstacle.
Right.
You basically like end that call to visit.
Mm-hmm.
Uh, it's actually I would say like the worst case time complexity would not change. Uh, yeah, I feel like I
Okay.
could be wrong there.
So the complexity for time does not depend on the number of obstacles. Is what you're saying. If k is not in your formula, you're saying that this does not depend on the number of obstacles. Is that the interpretation here?
Okay, let me just
Yeah. Have a
think
moment. Think
again.
about
So
it. Have
let's
a
say
moment.
everything. Yeah, so let's say if everything was an obstacle, like apart from the beginning and the end. So in that case, like you wouldn't go anywhere. So there's definitely like some involvement of obstacles. Like if I had to guess, it would probably be n square minus k. But mm,
Is that okay? We can think about that, right? So let's say we can think about the limits, right? Let's say that every single item was an obstacle. So k equals n squared.
mhm.
What's the time complexity there?
It would be pretty much constant time.
Okay, let's say now that instead of k equals n squared, let's say k is proportional to to n squared. Let's relax it a bit. So previously, if it's equal to n squared, that makes sense. It hits the edge case, right? Oh, 1. Okay, that's correct.
Hmm.
Now let's say, there might still be, a path, maybe two paths, but because k is approaching n squared, that is right. You can think of k being relatively dense, right? There's a high density of obstacles.
Hmm.
Do you think in that
I would
scenario?
say,
Yeah.
yeah, I would say it's gonna be like pretty much the same, like O of n square. I mean O of one, like constant time, because as soon as like you hit the obstacle, there's like nothing more for that path to traverse. Uh,
Okay.
no, wait, but that doesn't make sense, does it? Even if you have proportional. But the thing is, even if you have like a single path
Mm-hmm.
from the start to end, like the complexity would be O of n, I guess, at best. So like
Yes.
even if there's
Mm-hmm.
like one path, like you'd have to go like from the beginning to the end, which is like 2n, I guess, like O of 2n, which is O of n.
Mm-hmm.
Uh,
Over to yeah, yeah. Okay.
yeah. So let's say let's say the complexity. So you're saying if the number of obstacles is proportional to n square.
I'm thinking out. I'm basically giving you ideas to either help you build confidence in your time complexity or for it to refute your current answer, right? So one thing we can think about, of course, is a limit. The limit as k approaches n squared. You correctly identify once it equals n squared, it is obviously O1 because you hit the base case, right? But that's not too exciting. So what if for example,
Mm-hmm.
k is very dense, it's very high, it's near n squared, and there might be, let's say we know that n is 10 million and there are two valid paths. Okay, how long would
Mm-hmm.
it take for you to find the two valid paths?
It'll take off n time.
Okay, and can you explain that?
So yeah, so as I said, like we will have to look at the worst case time complexity. So uh let me just like draw an example. So let's just like imagine like all these zeros are like just ones, and let me just like make all these like zeros. I mean, yeah.
Mm-hmm.
So even in this case, you could probably argue that the number of obstacles is like O of n square.
Yep.
Uh, but you still have to like the worst case complexity in this case would be actually like a path, like a so this is a path, and this is gonna take like O of n time.
Mm-hmm.
So so yeah, I think it's not gonna be n square minus k or n square by k. Uh,
Okay. This
yeah,
is
it's
this
not
is
gonna be
pretty
either one of
this
them.
is pretty good intuition right here, right? Um, what we have deduced that in this scenario, if k approaches n squared, but is non-trivial, right? So that there's still a path. Maybe we could call it a constant number of paths, right? So there's a constant number of answers. In this case, you are correct in saying that the complexity would be O of n, and I'll help you by saying that the reason we know it's O of n is because we will never take we will never take a non-constant number of branches, right? So in this case, we will take no branches. There is no choice. There's only one path, right? If, for example, there are
Mm-hmm.
two valid paths, so for example, I'll give you this, right? In this case, there are two valid paths, right? This
Mm-hmm.
k is still approaching n squared. You can imagine we extend this out to infinity, right? So like 10 million by 10 million, but we still have this corner.
Mm-hmm.
That's still k is approaching n squared, but there's a constant number of paths, and so therefore we know that, and so in this case we know that there's a constant number of branches. There's one branch here, right? So it's not necessarily the
Okay.
case that it just has to be one path, meaning it's O of n. As long as we know that it's a constant number of paths, it's still O of n. Can you continue that?
Yeah, that's right. That
Yeah,
makes sense.
that makes sense. Can you continue that logic? Can you formalize that into an explanation for why you think that it's this solution instead of this one? In other words,
So
we, we,
if
we, we know
mm,
that. Oh, in other words, we know that this top solution is likely not going to be very correct because we have just disproved it with our
yeah,
corner example.
yeah.
So can you extend
But
the bottom solution to be correct for to be, and we know that the bottom solution is correct for when we have k approaching n squared. Can you now, also show or disprove that this bottom solution works or doesn't work for if k doesn't approach n squared? If k is small, for
no,
example.
but if k is approaching n square in this case, like this would be O of one, right?
Yeah.
But that's not the right answer.
Mm-hmm.
So see, it's I mean neither of these are correct
Mm-hmm.
because so if we have something like O of n times it's a number of paths, number of valid paths by k, something like that. What am I missing? So so if the number of valid paths is constant, in that case, we know that uh, it's a O of n solution.
Mm-hmm.
If the number of paths is n square, I mean if the number of paths is like linear, in that case, like it is a O of n square solution. So can we find a relation between number of valid paths and number of obstacles? Uh, that's one thing we can do. So so the number of valid paths, is it just like the number of, is it n square minus? No, that would make sense.
What was your idea there? There's I'll give you another maybe a bit of a hint. The answer to this question is not it's not super easy, not super trivial. Um, it's there's two ways to solve it. Well, I wouldn't say solve it. There's two ways to think about it. One way is to think about it the
Mm-hmm.
way that you've been thinking about it, I think, which is to consider the problem space in terms of the number of paths, which is good, which is cool. That's one way to do it. Another way is to
Mm-hmm.
kind of think about the two extremes and then finding a function of k that will satisfy both extremes and is still reasonable for the intermediate values.
Mm-hmm.
So you are correct in that if k equals n squared, k approaches n squared, then n squared divided by n squared does not equal n, right? It equals 1.
Yep.
That's a problem. Now, the obvious question is what function can we put in there to make n squared divided by something equal n?
I mean, it's not gonna be n over k, right? I mean, it's not gonna be n raised to 3 over k, would it be?
What's n squared supposed to represent?
It's the... Oh, is it just like n something like this? N square is the input space. So it's
Okay,
like the
input
number of
space.
uh yeah, it's the number of what do you say? Just the number of input elements.
Okay.
And so if let's say n was I mean if k was uh in the order of n square, you would have
Oh, I see
an
what you're trying to
O
do.
of n, but that doesn't work if k is constant.
Oh, I see what you're trying to do. So you're trying to say in this formula, if k equals n squared, you'll equal n overall, right? Is that the goal here for putting this arbitrary in there?
No, I just like trying to
Okay.
see where I can go with it, but
Okay.
probably it's not right, I know. Because if k is 1, then you would have like n raised to 3, which is like that, not the right answer.
Can we modify k instead? Can we
Sorry?
modify k instead? Instead of increasing the
Can we
numerator, can we
modify?
decrease the denominator?
So he's saying, I mean, we could have like, I don't want to
Okay.
introduce like a log term here because, I mean, in this case, maybe, yeah, so if k is the order of n square, we would have like log n square, which is uh log n.
Okay.
Actually, no, there's no use of
That's
yes.
pretty. Okay, you know what? Following that, following that train of thought, that's a pretty interesting idea as well. Following that train of thought, our problem is a square, right? Our problem is a square, which is cool. And if I look at your example, let me think about how to phrase this. If you look at your example, you have like the like as k approaches. Oh, okay, what's the best way to phrase this? I have to think about this in a bit too. If k approaches n squared, there's a pretty naive way to treat k. Um, to essentially treat k as if it doesn't exist, right? I think like for example, these are the two edge cases that we're trying to resolve. Can we think of like a middle case that will help you find a function? In other words, can
So
you
I'm actually just gonna express.
sorry?
Mm. I don't know, go ahead. Whatever.
Okay. So let me see what we're writing here. If k
Yeah, I
produces n
was just
squared.
saying
Oh,
that let
okay.
me explicitly like write down what we like had. So
I
if
think you
k
miswrote
was
this one.
oh yeah, it's-
Yeah. Kn. Yeah.
if k is n, like for a middle case, that's what's gonna happen. So uh, uh let's say this entire rows, but it'd still be O of n square, I think.
Do you want to elaborate a bit on that one? I like where you're going with that one, but I want to hear a little bit of reasoning.
Yeah, so let's imagine like this entire thing. Like if you look at C, if this entire thing was, let's say, just obstacles,
Okay.
and this thing was also an obstacle, so you'd be left with like a n minus one by n minus one grid, and I mean approximately n minus one by n minus one grid, and that's like O of n square minus 2n. So it's like again O of n square kind of.
Mm-hmm.
So yeah, that's where I got it from.
Okay. Let's. Okay. Let's see if we can. Okay. One thing which you haven't considered much yet is for the especially for these middle cases is one thing I think can help your explanation is we haven't talked about the positioning of k, like how where these obstacles are positioned, right? Because in the limits
Hmm.
the positions don't matter. Like if k equals
Yeah.
zero, then there's nothing to discuss. If k equals n squared, nothing to discuss. If k equals n, um, that's not like this middle case is not very well defined, right? Like if you think about it, we can define, we can put in obstacles. We can put in obstacles to trivially make the answer zero,
Hmm.
right? We can also make the, and as you said, right, if you were to randomly distribute them, then likely it will still be n squared.
Yeah.
So in other words, we want to just talk about potentially some sort of function which makes it such that everything is n squared, right? No matter what k is, it's n squared until k approaches n squared, in which case it very sharply decreases to n.
Okay. Okay.
That's tough. Okay, look, let's pause
Oh,
here. Let's pause here for a complex analysis. I think you know what you're talking about at this point. I think I know. I think you got the idea. Um, can
yeah.
we can we also just before we end, before in the can we talk a little bit about um, the space complexity in the edge, like just in the limits, just in the limits. If k approaches n squared,
Hmm.
what is the space complexity here? Can we just quickly go over that before we yeah.
Sure. So let me just think about the worst case. Uh, so in the worst case, the starting and the beginning are not zeros, so you'd still call visit. But since it is in square, you would pretty much never go in here. So the space complexity when k is approaching n square would be constant time actually, because most of the spaces, I mean, in most of the paths, like you'd pretty much return.
Mm-hmm.
So you would just uh set most paths to like just one,
Okay.
and I mean most paths to like just zero
Uh huh.
in the hash map,
Yep.
and yeah.
But is that O1?
Uh,
If there, let's say there is, it's approaching n squared, so there still is a solution. Is
so
this?
it's actually linear time.
Yeah,
Never
there
mind.
you go.
Yeah,
Oh,
it's
well,
linear time.
we're talking about space here.
It's the
Yeah,
same
yeah,
thing here.
linear time, linear space.
Yeah, the same thing here.
Yeah, because one thing you notice here is that a key I guess aspect of this problem is the fact that every time you iterate onto a cell, that costs you one time, right? 1 unit of time, but that also costs you 1 unit of
Hmm.
space. So in other words, your space and
Yeah,
time complexity are actually directly tied together, because you basically
yeah,
walk over every cell once for right that you visit,
that
right?
makes sense. Yeah.
Okay. Let me just think about this. Let me just check my own notes here. Give me a half a second. Very unprofessional of me. I apologize. Yes. Okay, that's all I had for this problem. So let's end the mock here. I wanted to first of all just say nice job. This is actually one of the optimal solutions. Memoization here, the bottom up approach, I think was very well done. Um, and so first of all, yeah, congratulations. This is a good solve. This is a solid solve. And the follow up I asked
Yeah.
was deliberately difficult
Hmm.
because I felt like you had too much of an easy time walking through the solution, and so it was
Okay.
we did a bit of gaming at the end there. Okay, so round of applause to you. Great work on that one. Can I just start? No, I like to kind of wrap this up just saying like, how do you feel, and then based on that, I'm gonna give some feedback on this one. So let's hear from you first.
Oh yeah, I mean, I definitely felt like I messed up the time complexity. I mean, I know that I usually ignore the time complexity when I like solve lead code problems.
Mm-hmm.
I mean, I just know on a superficial level like what the time complexity is, but I never thought about, let's say, the number of, I mean, the time complexity when you consider the number of obstacles as well.
Have you done this problem
So
before, like a similar one, or this one? Have you?
I'm sure I've done many lead code
Yeah,
problems. I'm sure I've
yeah.
done something like this
This
before.
one's a pretty common problem for those in the audience as well. This is a
Yeah.
pretty common, not the follow up. Okay, the follow up was, I admit that was kind of mean. I meant like this problem in terms of counting paths. Okay, counting paths in a well defined space. In this case, a 2D matrix. Right. This is a very common problem, and I think at least the base problem, like how to actually iterate through things, how to actually do what's going on. This was very well done. Okay, so first of all, I think just to kind of get out of the way, the actual solve, I think the expected level of performance was definitely achieved. So great work there. Let's quickly go over
Right.
some of the feedback I have before I forget and before we run out of time. Okay, so the first thing is, yeah, some interviewers will just paste you the problem, like into the coder pad. You read it and
Mm-hmm.
you write it. Um, Sometimes it won't, and the reason that sometimes people
Mm-hmm.
won't do that is because part of the exam is to test your ability to, like, not test your writing skills, but testing whether or not you can recognize that there are things left out in the problem, right? If there were any information
Mm-hmm.
left out in the prompt description, that's more easy to detect if if they don't if they aren't able to, like, basically go back and see the entire prompt description at the start, right? So just know that, yes,
Mm-hmm.
I wouldn't say it's as like, yes, honestly, it's not as common as if they just gave you the written description, but this is part of the exam. Okay, so
Oh,
I
that makes
would so
sense.
if you're unsure, just stop them right away. Just say, hey, I don't see a prompt. Are we going to be dictating this? Do I need to take notes? So just stop them right at the beginning. Saves everyone time. That's not rude at all. So just be aware of that.
Mm-hmm.
Okay, that's so. But after you got that, everything was good. That was good. Example was good. Intuition with memorization is good. And I think the explanation of memorization was a bit confusing there. You were going back and
Mm-hmm.
forth a bit about, oh, DP, oh, top down, oh, bottom up. You didn't actually say, okay, my approach will be using bottom up like this. Here's how I'm gonna do it. So you didn't actually say. You kind of just kind of fluttered a bit around both options and just started doing something, right? So the explanation there, you
Mm-hmm.
got to be a bit more explicit with. Okay, but once you did start doing the bottom up, I saw that was you set it up very well. You set up the helper function, set things up very quickly. That was good.
Mm-hmm.
Edge cases, right? Edge cases for the obstacles. Uh, Small nitpick. Generally speaking, you should clarify that all out at the beginning, like right after they finish the
Mm-hmm.
explanation. If you can, the benefit there is then it's a positive signal to for the interviewer to say, oh, this person is thinking about these edge cases, right? It's still
Mm-hmm.
okay, but it's not as good to say like, oh, I ran into this edge case when I was programming. Oh, now I gotta go ask, right? So at least you asked, but that's not as good, right? So if you had known about that at the beginning, just make sure you asked at the beginning. Another small
Mm-hmm.
thing is, I put it as a nit. I don't think this is a very negative thing, but this is a thing I noticed is you assume the matrix was square. That's not really a problem in this case because your solution works for both a square and not a square. And
Mm-hmm.
that's probably because you think you heard me say a square. I tried to say m by n. You might have heard me wrong. Not a big
Oh.
deal. But this is the thing, okay? With all matrices or like all inputs which can be ambiguous in dimension, you should
Mm-hmm.
ask. And one thing you didn't ask in addition to this is, well, you didn't explicitly ask, and it's okay for this problem is, the matrices and in general arrays in program languages can be jagged, right? Like
Mm-hmm.
jagged arrays. Like, are you familiar with jagged arrays?
Not
So if you look
really.
at your example C, right? If you go to Python, this is a valid 2D array, okay? And this is known as a jagged array, in that the subarrays
Oh.
or the dimensions of each of the arrays of your 2D of your matrix are not the same dimension. Okay, so
Oh.
so jagged arrays are a consideration. Now again, most of the time it won't really matter, but in this case your code would have broken. Okay, so in general this
Yeah.
problem doesn't matter, but you need to be asking these things just to make sure. Okay, so these are just kind
Mm-hmm.
of the edge cases for the matrices. You should just know them. There's like a couple of these edge cases. Just memorize them. Just bang them out right at the start. So a couple of these guys. Okay.
That makes sense.
One thing that was a bit more of a concern was that 1-3 confusion about you kind of got twisted up about what the number should be there. Um,
Yeah.
right. That's okay to be confused about that, right? I would spend a bit more time to actually figure out exactly what's going on instead of going back up to
Mm-hmm.
your code and start changing stuff. Okay. If I was a more evil interviewer, I was pretty evil. If I was an even more evil interviewer, I wouldn't have said anything, and I would have just let you change all your stuff
Mm-hmm.
up. I don't know what you would have done. I would have sat back and watched you do everything, and it would have been the exact same result because that wasn't an issue, right? So that's one
Yeah.
thing which you have to notice that you could have wasted a lot of time on that. So if you see an output you don't understand, make sure you spend the time to understand that before moving on. Okay.
Yeah.
Okay, so this part doesn't
Mhm.
apply anymore because you fixed that one. Time and space complexity, yeah. Time and space complexity was correct for all of the basic cases, and that's what I would expect for like medium level, medium difficulty elite codes. So I think first of all the takeaway
Mhm.
is you did well on that. Now one thing that people will start considering, will start asking, especially in follow ups, okay, is
Mhm.
problem descriptions that actually have multiple dimensions of input. Right. So for example, the only input to the problem is a 2D matrix, and so you're thinking, oh, the only input is in by n, right? But actually, the matrix has a special quantity, which is the number of obstacles, right? And so
Mhm.
it looks really good. It's a bonus point if you can at least specify that, oh, we have this quantity. I don't really know what's going on here. I need to think a bit about this, but oh shit, it's 6 p.m. But at least if you can state that, oh, another input isn't just the size of the array, but the number of things. I think that's a really really positive signal. And so the takeaway here for you, I think, is just to be very critical about what the input of your function actually is. And there might be some
Mhm.
hidden variables, such as what we discussed today. But I think given the time and given the level, especially consider you coded up very very quickly, and I was trying to find a appropriate but difficult follow up. I think overall this was still very well done. So everyone, round of
Yeah,
applause for Harsh here, and we got to keep the show moving because I was yapping for too long. So yeah, great job Harsh. It was nice seeing you. Take care. Okay.
thank you so much. Thank you so
Take
much.
care. Take care.
Bye.